taking automatic consent from everyone of being here. So welcome everyone. Day 2 of our continuing education credit blitz. It was an awesome day yesterday. We went through a lot of topics. Just to get squared away here, I'm going to give another intro again to maybe some new people. My name is Moose. Full name is Mustafa Hassan. My counterpart Emily Mellon is on a call with me. We're both consultant specialists with Delta Controls, smart buildings manufacturing company. Our role really is to focus on consultants in our territories. I'm based out of the East Coast, and Emily's based out of the West Coast, and we talk to consultants all the time. We help them with product specifications, continuing education credits such as these. We create content wherever they need in the industry, whichever part of the building automation industry. And a lot of our content, most of our content is AIA accredited, meaning you can earn credit by viewing our presentations. This way, today and yesterday, you were able to tack on 9 credit hours just through this blitz alone. We're going to get started here with BAS 104. There's your schedule. We just wanted to show you the schedule for yesterday as well. If you didn't make it yesterday, there will be a survey going out, so you can give your thoughts on whether you benefited from today. If you were there yesterday as well, you can also give suggestions on other content in the future. We're here for you. We're working around the clock to create beautiful content like this that's actually beneficial.
वो कल मैंने कौन सी डायरी ली हुई थी ये वर्ल्ड डायरी थी ना कौन सी थी कल वर्ल्ड डायरी मेरी
If we can remember to mute our mics, I'll go through and mute some folks too. But
Yeah,
quick reminder, mute your mic.
I tried to look for that setting. I couldn't find it where they come in muted. All right, you got it. People that are joining in, please join in muted. Thank you. So we'll get squared away here with BAS 104. So before we get started, if you have any questions about the topic, feel free to unmute and interrupt, leave a message in the chat. We'll be watching. I'm looking at the questions. I will stop and answer the question if I can. Yep, right away here. So BAS 104 is the final part of a 1 through 4 series. 1 through 3 were happened yesterday, and I'll briefly go over what those were about. So 104 is designing and integrating the building automation system, and the focus of the day is sequence of operations. So the reason we're able to provide you guys with continuing education credits is because we're registered with the American Institute of Architects, the AIA. One requirement that a lot of the content, all the content has to be non-commercial, products, no mention of companies, things like that. So it's strictly educational, and I think Emily and I did a great job at that. We're here to teach you guys. And all this material is copyrighted as of 2024. So the BAS series thus far, Emily took you guys through 101. That's how we started the series. In there, you learned what a building automation system is, the benefits. You looked at things like lead and well, of course, more generally. But again, you guys got a good intro before we took on 102 and 103. In 102, we looked at points and protocols, and we looked at your typical points. We looked at how to go through a mechanical schematic, and we looked at different things like pressure transmitters, pressure switches, differences between switches and sensors and whatnot. And then we looked at protocols and things that make up the network overall, like switches, gateways. Overall, those are all fundamentals of the building automation system. In 103, Emily last night took you guys through interdependent systems. Those are your mechanical equipment, like VAVs, chillers, cooling towers, boilers, how those all work, whether they're expelling heat from the building, or providing heat, or providing chilled water to the building. So you went through those, not necessarily the sequence, but again, what the components or your typical components are for control of that equipment. Finally, today we're going to be talking about sequence of operations. And kind of when I was making this presentation, it was supposed to be just the focus of sequences of operation, but I added a little kind of a prerequisite right before you really get into the sequence of operations, before you start using that data. There's also a a prerequisite to creating a data model. And that's what we're also going to be talking about today, because it doesn't just stop at automating your building. It doesn't just stop at sequence of operation. So we're going to talk about things like data models that feed into an actual smart building, where you're able to then trend points, schedule, alarm, create efficient alarming, and then eventually commission the building and deliver it to the customer. So there's your AIA agenda. So we're going to look at the process of designing a building automation system, right? The different pieces of equipment, sequences of operation. We're going to build those together. Emily mentioned yesterday that I will be going through some of those same schematics, mechanical schematics, and building the sequence of operation kind of line by line with you guys. Then we're going to take a look at the so we're going to look at the systems. We're going to look at the sequence of operations. Then we're going to look at the importance of standardized data modeling or point tagging, right? To in order to allow for proper data flow and usage, right? Because before you can use the data, it has to be defined, and if you can't define it, then you simply cannot really move it to. You can't actually program something if you don't know how to define it. And the focus here is standardized, right? One person can define it one way, another can define it another way. So we're going to look at today what's the importance of standardizing this data as a benefit to the building owner or operator. So, and then we're overall to end off, we're going to look at things like commissioning, testing, and maintaining a building automation system. Because once the project's delivered, we want to make sure this thing is actually going to function the way that it's programmed, the way that it's sequenced, and that the equipment is tested, calibrated beforehand off to the customer. Okay, so what is a sequence of operations? Right, so a sequence of operation outlines the functional steps a system or component will perform under specific conditions. Right, they serve as a blueprint for how your BAS or building automation system should operate in response to various triggers. Right, like temperature or occupancy changes. Right, and like Emily said, those are kind of your that's kind of one of the goals, right? It's occupant comfort. So a lot of those triggers have to do with enhancing occupant comfort or reducing energy usage, right, or optimizing it. And a lot of these steps, right, feed into the sequence of operations. But again, we can call them different things. This isn't out of a standards book, but the names are kind of self-explanatory here. So your control logic will define the order of operations and the decisions that the controller will take, right, to start returning that occupant comfort to a comfortable position. Maybe toggling off certain equipment when there's no occupancy. Again, reducing that energy usage. Right? Your set points are the target values, right? The specific set points, specific values of temperature, humidity, maybe lighting levels, right? Again, completely related to occupant comfort. Or again, energy usage. Right? Then you have trigger conditions. So a lot of these are interrelated, but you don't really have to follow the sequence this way, but it's good to know that these make up, right, every line in your sequence of operation. There has to be a reason you're trying to control a certain piece of equipment or a certain field device, right? And then your response action is things like opening a valve, toggling the thermostat, turning on the light, turning off the light, things like that. Also, just another disclaimer for those that went there yesterday. Remember, the building automation system doesn't stop at your boiler, your cooling tower. There are other systems like lighting or security that can also be integrated. So don't forget that. And we will talk a little bit about that as well. But of course, the major components of the building that usually people want to integrate or automate are your mechanical systems, like your boiler, your cooling tower, your heat, all your HVAC stuff. That's usually the primary thing that people want to automate. But there are other levels to it. But that's one consultant to another. They may be interested or may not be interested in that. So again, it's sequence is your most important aspect of BAS design. Having a well-designed building automation system sequence of operation ensures that systems like your HVAC, lighting, and electrical systems operate only when needed. It's going to reduce unnecessary energy consumption. And again, all these terms from 101 all the way till now are again very redundant. You've heard them so many times from Emily and I. Energy reduction, right? Energy reduction. You got occupant comfort, things like that. Those are all repeated, and that's because that's the end goal of a building automation system: reduce energy usage and occupant comfort. There really isn't much else that you're trying to automate a system for. But again, these are all just interrelated, and as we in 104, really, we're just going to get more granular, right? Figure out how to actually optimize those things, right? So the sequence of operation also ensures that all systems are going to operate as intended, right? As clearly outlined. by the control logic, the schedules, the system responses to various conditions. This is going to help them maintain optimal performance, and it's going to reduce wear and tear. So it's going to extend the life of the equipment, right? Having a proper sequence of operation, right? Also, you have consistency of system operation, right? In various scenarios, you have occupied, unoccupied, heating and cooling. That's all going to be outlined in your sequence of operation. And that consistency will help the operators manage the systems more effectively. Building engineer, maybe sitting somewhere in the basement with a workstation looking at different faults and things that are happening in the system. Having everything programmed or scheduled properly will allow them to focus more on one issue, right, or prioritize issues as they roll. And then finally, by carefully regulating the temperature, ventilation, lighting, things like that, the sequence of operation will help maintain optimal indoor environmental conditions. Okay? So again, you have occupant comfort, you have higher productivity and satisfaction in commercial or office spaces. This goes back to leading well, right? A lot of those standards are designed, you're designing buildings around, again, the occupant comfort, looking for better ways to enhance productivity in the workspace. Because as tenants move into a building, right, they are looking for things like that. Right, this will actually allow tenant retention. You have higher rental rates, right, in a building. So it is very attractive for a building owner to have a building admission system. Those are all things, again, mentioned by Emily 101. And I also will be mentioned again in building wellness later on today. And finally, last but not least, and this is extremely important as a designer when you're dealing with an owner or a customer, by ensuring a proper sequence of operation or ensuring that your system operates efficiently, you're going to minimize energy costs, and you're going to get your customer your highest ROI, return on investment, right? Because you can spend the money now, but with no data coming in, with no information on how the building is actually performing, then it's just money wasted, right? You spent a lot of money on automating all these systems, throwing controllers everywhere, hardware, field devices, but you don't really get any information back. It's really just a waste of money. So there's a lot that goes into it. And again, as I mentioned, sequence of operation is not the end goal of optimizing under buildings. So here's an example of a basic sequence of operation for an air handling unit. We're going to get a little bit more specific with the VAV later on, but we're just going to run you through the steps we mentioned, the control logic and things like that. So an air handling unit might be set to maintain indoor temperature based on set points, right? So let's read through this. So for example, so the air handling unit, it's maintaining the indoor temperature based on set points. When the temperature rises, right, above the set point, we're going to stop here. There's your trigger, right? Your temperature rises, right? It's a very basic concept. So because the temperature rises above the set point, you know, there's your set point, and this is probably referencing, it's pretty obvious, referencing the indoor temperature, right? So as the indoor temperature rises above a specific value that's calibrated at the controller, the air handling unit will activate the supply fan and open the chilled water valve. There's your control logic or your response, right? So those are the steps that the system is going to take to get back to that optimal indoor temperature. Right. So very basic. You have rising indoor temperature. The system is going to open the chilled water valve and increase the cooling up, right? And then later on, take it one step further. It doesn't just stop there. We're actually going to keep the valve open and keep using energy as the temperature reaches the desired set point. Then the fan speed and the valve positions are going to adjust to maintain comfort. Look for that bridge between comfort and conserving energy. If you don't no longer need the cooling output, let's close those valves. Let's ramp down the fan speed for the air handling. Also, very importantly, working along with each other are VAVs and air handling units. And again, this is mentioned Emily yesterday. So I'm not going to get into a lot of detail. We're going to jump right into a sequence of operations here. But remember, an air handling unit will feed the entire building, and the VAVs will be spread all over certain spaces, right? Adjusting their damper position to allow specific CFM to whether they want to increase the cooling output in that space or not. So this is a schematic for a cooling only needed feed box with zone occupancy monitoring, right? We're going to go through the sequence of operations here together. The sequence of operations is not shown in front of you guys. I'll read through it, but you'll see some animations that will help you point at the section I'm referencing, okay? So each VAV unit will be directly controlled by its own dedicated EMS controller. There's your DDC or building management EMS controller. There's your DDC controller. That's where everything comes back. The field devices are wired to it. And in this scenario, this is probably not a building level controller, right? This doesn't really need a lot of supervisory or doesn't need a lot of horsepower or a ton of inputs and outputs. But yeah, so well, in this case, it's probably an application specific controller, right? Just because you have additional things like your occupancy sensor, right? This is more than your typical points for a VAV. So maybe an application specific controller will suffice. So again, there's your DDC controller. Now your DDC controller will be connected, at least for the VAV space, it will be connected to a wall-mounted temperature sensor, right? With integral relative humidity sensor. Okay, and now it says temperature sensor. It doesn't say thermostat, but I see a slider here, so it's probably also a thermostat. So you can adjust the output from here, or you can adjust it through the controller, right? Through your sequence of operations, right? Next up, your zone occupancy and vacancy will be actively monitored by connection to the lighting control system. Okay, so you have a zone occupancy sensor, which will allow the VAV to allow air in or to ramp up its CFM based on if you can entering the room or not. If nobody's using the space, then the damper will close. And we'll see that a little bit. Actually, we'll see that right here in the next step. There's your damper, right? So when the zone is in an occupied mode or an after hours mode, based on this occupancy sensor here, right? The VAV damper will be modulated to maintain the zone, a specific zone CFM setting. Okay, so that value will be set up, right? Unless vacant mode has been triggered. So unless this occupancy sensor doesn't feel anyone in the space, then the damper will probably close to a minimum, right? Again, those are based on standards that Emily referenced yesterday. There are standards that don't allow you to really close the damper fully, right? Because there's a minimum amount of airflow that has to be flowing in the space. During the unoccupied mode, then the VAV damper will modulate back, will go closer to close, but again, not fully closed. Now, how do we manage the cooling or heating, right, in this space? If this VAV had a heating coil or the air handling unit is pushing heated conditioned air right through the space, well, the controller is going to compare. This is your controller. It's going to compare the set point with the space temperature, right? So if it needs cooling, then it's going to modulate, and if it needs heating, it's also going to modulate and allow the specific air to flow through until the desired temperature is reached. Okay. Then finally, your DDC controller is going to monitor a lot of points, right? Like shown here in the points list, things like airflow set point, fault signal, right? If things don't end up working, these are all, I wouldn't call these inputs. Some of these can be actually done virtually, right, through a program. That was your VAV sequence of operations. We're going to talk a little bit about lighting and occupancy briefly here. So occupancy sensors, as shown on the previous slide, there was an occupancy sensor there, and we use that along with our HVAC system, our VAV system, right, to adjust settings based on movements, right? So, again, I'm not going to go deeply. This is pretty self-explanatory, but when the room is occupied, you can dim the light, right? You can turn down your HVAC systems. You can reduce air conditioning, maybe modulate the VAV back down to a specific CFM, lower the energy usage, right? This is, of course, great for energy efficiency, right? So an example of a sequence of operation for lighting integration with occupancy, right? All the lights are off when the space is unoccupied. If the occupancy sensor detects movement, it's going to send a signal to the lighting control system, and then the lighting control system will turn on the light, right, to a predefined thing, right? 0 to 100, that can be proportional as well. Now, here's the best part. If you incorporate daylight sensors, right, into the space to adjust for natural light, then you get even more optimization, right? So you don't have to turn on the light up to 100% if there's daylight outside, right? You have the windows open. So if you have daylight sensors, right, you can use daylight harvesting, right? Depending on the amount of natural light available. If there's sufficient daylight, the light's made into 50% because there's already control sensor, right? And then continuously monitoring occupancy to adjust for the light in the space. One note here, and this is kind of a segue into the artificial intelligence presentation. It's going to happen later, I think around 3 o'clock. So occupancy can also be estimated through machine learning. And I'm not throwing that word around because it's a buzzword recently, or because we have a stock that we want to, raise the prices up. But yes, occupancy can be estimated through machine learning through a combination of parameters like temperature, humidity, things like that. So a lot of that stuff goes into algorithms and can actually, and again, estimated is underlined, right? Because it's not calculated. I don't want to say exact occupancy can be counted, right? But it can be estimated through certain thresholds, right? So if you haven't signed up for the artificial intelligence presentation, you probably should. There's a lot of exciting stuff there and things that are already in the field of controls, right? This is not hypothetical. These are things that are out there today in the world of controls. You should probably sign up for that. Chillers and cooling towers are also two systems that are always, like not always, but they're, they work together to expel heat, right, from your water system to allow chilled water to reach the building. And your cooling tower kind of expels the heat from the chiller supply. So they work together. And again, Emily referenced these two systems, and right in a second, we're going to go through an air-cooled chiller example. But in this case, this is how the building uses water, right, to regulate cooling for the building. Right? So your cooling tower takes the heat out, and then your chiller supplies use pumps to supply chilled water to the building. So the difference between this air-cooled chiller and the last example is that the last example a chiller needed the cooling tower, right, to expel the heat through the water. In this case, it's an air-cooled chiller, right? There it is. Now, Emily showed this schematic yesterday without the sequence of operations. So today we're going to build it together, and we're going to look at the components, the field devices that make this up, and line by line how the system actually operates in the field. So the chiller and the chilled water pumps are controlled by the VDC system. There's your chiller. If you didn't see it yesterday in 103, it's an air-cooled chiller, and there's some notes there that it comes with a BACnet MSTP interface by the chiller manufacturer. That's a great point there. So it's directly indicating, saying, hey, you don't. This is provided by the chiller manufacturer. You don't need to go ask around. You don't need to send in an RFI to the designer, right? I'm talking as a controls contractor. If I'm estimating this, for example, right, to send an email to the engineer, it sits right there. The BACnet interface is coming through the chiller manufacturer. So I know I need to run a communication point back to my DDC controller, which is shown down here. Okay. There are your chilled water pumps, these two. And I'm assuming that, they're going to be using some type of a lead lag sequence here, right, to reduce wear and tear on one specific pump. They want to have the runtime of each pump equal the other, right? So not one pump is working harder than the other, or maybe if the set point really goes really high, then maybe both pumps would be used to allow specific chilled water segment. Now, how do we know if the pumps have started or not? Well, do we flip a coin, or actually, we're talking about control systems here. There must be something that's out there that's going to figure out, whether the pumps are on or off. So we're going to get to that in a moment. But when will the chilled water pumps, when is this system going to actually activate? Well, it's going to go through a time schedule program, or when the outside air temperature, right, is above 65 degrees, and 20% of the chilled water valves are calling for cooling, right? So, or the chilled water valve is calling for 20%, which that's how much the valve position is open, right? So if the valve's at 20%, then we know we need to ramp up the pumps. But also with other conditions like the outside air temperature being above 65 degrees. Okay, so again, how do we know if the pumps are on or off? Well, there's going to be current switches at each pump, right? And that'll tell us, right, the status of the pumps. The DDC system shall monitor the chilled water supply and return temperatures. There is your chilled water supply. Water goes this way, right? And there's your chilled water return. So there's two temperature sensors on each line. And then it's going to enable the chiller when the chilled water pump is proven on. So there's a condition that the chilled water pump has to be on for the chiller to activate. All right, this is probably safety to make sure that chiller is not just running for no reason, that the system's actually calling for a chiller. Next, the chiller through the self-contained factory controls will maintain the set point set from the DDC system, from the BLITZ system. Right. So there's the self-contained factory controls, right? And the sequence matches perfectly the schematic here. So there are self-contained contained controls within the chiller that allow it to operate the way that Emily explained to you guys yesterday. And we know that the interface is provided by the factory. So again, we're going to run a communication point and retrieve a lot of data. Leaving a chilled water temperature set point, so leaving the chiller will be reset, right, from a certain range of temperature, 50 degrees to 60 degrees, and that's adjustable as ambient outside air temperature varies between 80 degrees and 70 degrees, right? So you don't have to remember these exact values, but I'm just trying to help you build the sequence of operations in the space, right? Now, I mentioned lead lag, and there's going to be lead lag software for units having multiple pumps, right? So again, it looks like they want to run lead lag, meaning one pump will run and the other one will wait unless needed, or they'll trade depending on the runtime of one specific. Or if the lead pump fails, then the other one will be commanded. And there's going to be an alarm that's going to come back to the operating workstation, right? So there's a lot of points happening here. So, and then a lot of points are going to be A lot of points are going to be, it's shown here at the bottom. If you could read this, then refer me to your optometrist because I need those glasses. But there's all these points in this area basically showing you what should be read at the operating workstation. All those points, all field devices that are wired up here, all the virtual points that the technician is going to be programming into the controller. Well, this is what's available, and I'll read some of them for you guys. So those points, an alarm from the chiller, right? That will come directly from the interface. It will tell us whether the chiller is operating or it's at fault. There's something going on. It's not working. You have the current status, right? So are the pumps on or off? You want to know that status at the operating workstation. And what will provide that is the current status, the current switch at each pump, right? You have your chilled water supply and return temperature sensors. Both of these will be monitored and give these temperature sensors. And then you have a chiller alarm status. Again, that's the same alarm coming from the control panel of the chiller factory controls. And then pump and chiller runtime. You want to know how long each pump is running for, right? Up to 64,000 hours. It's specified up to 64,000 hours, right? Need to be logged. And then you have some trend logs, alarm history, and then lead pump indication, right? Which one is actually the lead pump in the system? There was your chilled water supply system that we're looking at, the boiler. And again, Emily mentioned this is your system that's going to be providing heating throughout your building, and it works in tangent with a lot of other equipment. In this scenario, we'll get right into the sequence here. So this sequence actually will be built on the screen as I go along. So your boiler and hot water pump are controlled by the VDC system. There is your boiler, and there is your hot water pump. Okay, there's a singular hot water pump here. See a lead lag need, but what we're working along with the sequence of operations. Okay, it also mentions that the boiler control panel comes with a backnet interface from the boiler manufacturer. So I like this note a lot. Again, it makes it very easy. Okay, I know that I'm going to run a communication point, right? Or well, depending on how it's written, but it could be hardwired. It could be a communication, like a backnet point, run straight to the panel to collect information from that boiler, right? Your DEC system shall monitor hot water supply and return temperatures, right? And start the boiler to maintain the set point. There is your hot water supply temperature. There's your hot water return temperature, right? Our water is flowing this way to the building, coming back to the boiler this way, right? So reset the heating hot water temperature set points from this range, okay? As the outside air temperature varies from this range. Upon a call for heating, energize the system hot water pump. Again, there's your system hot water pump. The status of the pump is provided through the VFD interface alarm. So there must be a VFD for this pump, and we're going to run another communication point to that VFD and collect information on that pump, whether it's on, whether it's having a fault, what the speed of the pump is, and then also if the pump is in fail mode, right? There's something wrong, that's going to send an alarm to the workstation. The VFD on the system hot water pump will modulate, right, to maintain a constant differential pressure set point. This differential pressure sensor or transmitter is not shown here. It's probably somewhere down the supply line, right? Usually 2/3 downstream. Or if the consultant gets really specific, then he's going to look for exactly where that real the need or demand is highest, and that's where that differential pressure will be. Boiler is enabled only when the following conditions occur: the time schedule is on, the outside air temperature is less than a specific set point. It's right here. There's your outside air temperature. And when any of the hot water valves demand heat, either in occupied or after hours. This valve is, again, not shown here, somewhere down the building supply line. And if it calls for heating, that's when the boiler will turn on, right? So that's how a general sequence of operation builds, right? It depends on need, depends on how you want to control the system efficiently. And again, it depends on what the heating supply looks like in the building. And then the following points will be displayed on your operating workstation or at your, will be programmed also through your controller, right? Now, a lot of these points are hardwired, real points, and some of these are virtual. Virtual could be like your runtime, right? How long has this pump been working? How long has the boiler been working, right? But in this case, there's no really lead lag. So there's no alternating between this pump and another pump, right? So a lot of these points will be, all these points will be visible at the operating workstation and monitored through these devices laid out here or through virtual points that are created by the controls contractor or technician. Now, these points shown here, right, I like these points a lot. This whole schematic just makes it so easy to estimate as a controls contractor, to put a good budget on it, but also to remove confusion between the controls contractor and Division 26, or maybe your mechanical contractor. Like, who's going to wire this stuff? And when it's shown here, it's pretty straightforward, right? It strictly says that this is an output, this is an input. I'm taking these, I'm tallying them up, and I'm putting a price to them, right? So I can send out that price to the GC or to the mechanical contractor, on time. Those were really the focus of the presentation, was building those sequences of operation, and again, showing you like past designing the equipment that actually sits in the building. It's how you control that specific equipment, how to build a sequence of operation. We're not going to teach you word for word what to write, but just the logic behind it, how your mind should work, right? Maybe putting certain safeties in place to make sure that systems, if they're in failed position, for example, you have some sort of alarm come back to your operating workstation. But now we're switching attention here to kind of an addition to sequence of operation, or you can think of it as also a prerequisite for a lot of things, right? So we hypothetically automated our entire building system. Great. So are we done now? Like, do we just pray and hope that it all works? No, not really. Right? We got all these systems running through a specific control logic. Like, what if they malfunction? We have things like trending, schedule and alarming. This is a prerequisite to all of this. Right? The next step would be to start collecting data from the system, right? The temperature, humidity, all those points would be trending, right? What does that mean? We'll define really the trending part a little later. It will set up alarms that are going to come back to the building operator, right? Based on certain circumstances or conditions that happen in the field, malfunctions. A prerequisite for all of that is data in the data collection is choosing a standardized way of defining each object, right? The VAV supplier temperature sensor, right? The air handling unit that's feeding the specific VAV, right? So a standardized way of defining each object, piece of equipment, or even that field sensor. Right? This concept is called semantic data modeling, or for simple terms of what we're going to talk about today, tagging. Right? We're tagging each point, right? So, and simply put, if you can't define it, you can't monitor. Right. And we'll give you guys some reasons here to listen to this because it's a little bit boring, it's a little granular, but I'll blow through it just to give you guys a bigger picture, right? And especially if there's any specifiers, any consultants on the call, what do I do with this information? I'll give you guys that. Right. So reasons that you will want to look at semantic data model, right? You can get things like in the IoT in our artificial intelligence space in the control world, you get things like predictive maintenance, right? You're leveraging IoT sensors and AI algorithms to forecast equipment failure before it even occurs, right? This way you're reducing downtime and maintenance costs. Real-time data analytics, where you're enabling constant monitoring of energy usage, environmental conditions, and equipment performance, which is going to facilitate immediate adjustments for optimal efficiency. Then you have adaptive control, right? AI-driven building automation systems can dynamically adjust the settings based on occupancy patterns, weather forecasts, and usage trends for energy-saving benefits. You also have things like edge computing, right? With examples of that, local or on-site data processing, right? This way you're processing data locally, right, at the controller, rather than sending it to the cloud, which is going to decrease latency and enhance, doing it locally at the controller will decrease latency and enhance control over real-time in the building. You also have improved reliability, right? Edge computing is going to ensure BAS functionality, even during network outages, and it's going to maintain critical operations for uninterrupted system performance. And then last but not least, and this is a big one, it should be, it's cost efficiency, right? You're minimizing cloud data transfer needs. It's going to help reduce operation costs, and it's going to ensure faster response times. So those are all reasons to listen to the gibberish I'm about to fill chance. So with the importance of semantic data modeling and tagging, right, you have here a building with different equipment and sensors, right? And in order to really write a proper control logic or sequence of operation, you'll put it into the controller from which you'll collect data and start generating reports, sending them to your building owner. You need to define relationships between these different parameters, these different objects, right? Like the air handling unit, the VAV. So here we don't really know. We only know that the air handling unit is feeding the VAV and the VAV is, feeding those specific spaces. But what about all the sensors, granular stuff, right? And you have to also standardize the one person is going to write it this way, another person is going to write it the other way. If for whatever reason those two vendors come together in one building, their systems are just not going to read each other's data, So that's the importance of this. So what is tagging? It's an effective way to create a relationship, right, between items without the need to actually understand the underlying information. So you're connecting different objects or parameters. In the physical world, we see tags all the time without noticing, right? When you're celebrating a birthday or a wedding, you get a card from the local store. The card has information on who it's from, who it's intended for, also what the card is intended to celebrate. At any store or market, your barcode or your UPC, your universal product code, those are all forms of tags. It's tagging the item, right? That's feeding into the scanning system, and it's telling you all information of the product, price, category. Is there a sale on the product, right? So those are all, those tags give you that type of information. If you have an Instagram and you use social media hashtags, right? Hashtags are another form of tagging. If you're trying to share information that relates to a certain interest, right? But the issue with that is that you can just shoot a million hashtags to one specific picture or object, and that'll kind of dilute the information. So if you don't have a standardizing model and everyone's using it the same way, the information is going to get skewed, right? So now that's our world, controls world. How is this all relevant to this, right? In the world of building automation systems, the tags are going to identify, again, the relationships between various pieces of information. I can tag in their heading, and then I can tag a VFE that the unit feeds, and then I can also tag abstract items of schedule or temperature. And that's how you build a sequence of operation properly. Take a look at this trend. Okay, AHU1, VAV2, SAT. Can anyone tell me? You can unmute or you can send it in the chat. Can anyone tell me what you think this trend log is referencing? What point in the system this trend log is referencing? You can just unmute and say.
The VAV2 supplier temperature sensor,
VAV2 supplier temperature. Okay. Yeah, I mean,
which
at
is
least
being
from
fed
our
by
knowledge,
Yeah.
AHU1. Correct. Correct. So that's one way. Okay. Some people will say this is, and you know, some are more obvious than not, but some will say AHU1, right? This is the supplier temperature coming out of AHU1 feeding into VAV2, right? So yeah, you may say, oh, that's not likely. I know, I mean, the people I've been tagging with, usually this will be what Mirza just mentioned, right? So that's the whole point, right? It's the different interpretations, right? Because if somebody else tags this as that supplier temperature for the discharge temperature for AHU1, then there's again a confusion, right? So me and Mirza have to agree, right, on a way to actually, okay, this is the supplier temperature for VAV2, right, which AHU1 feeds. Right? But if that's the supplier temperature for VAV2, why are you mentioning AHU1? So again, we need to standardize, right, how we tie it all together. So by adding context to the data, right, we gain more value, right? And what's inherently missing in strict metadata is the relationship between entities. That's what's being highlighted in the slide, right? At different levels of information, you get different relationships. The VVs have different points, right? Like airflow, damper, occupied mode. You're tagging these, okay? Then you have an inherent unit, right, which feeds different VAVs, and you're adding more tags, right? This is how you're going to get a nice equivalent summary. So the more tags, the more relationships you add, the more inherently, the more coherent the data is going to be. Let's get to the end of this, okay? So as a specifier, you should be involved in this side of the data usage, because this is how you get your customer the best ROI, best return on investment. It's not by simply specifying some hardware and calling it a day, right? After automating the building, your customer wants to study building performance and reports, right? They want reports to be simplified. You want to be able to actually know if this BAS that I spent so much money on is actually going to get me money back over the years. Right? And that's all going to start with a proper data model, or in specific terms, we're going to introduce here a standard ontology. Okay, so ontologies are the end goal of what we're talking about here, right? It's actually a semantic data model, right? Those are examples of semantic data models, right? So one ontology is called BRIC. Okay, this is a public, right, ontology that you can use to model your data, right? There's another one called FaceTime. In this case, this is how BRIC, right, talks about relationships in the system. Rooftop unit 1 feeds VAV5. VAV5 has point, right? These are all standards, right, that BRIC uses, right? It's called has point. So VAV5 is self-explanatory. VAV5 has point, whatever that is, it has point discharge air temperature. So it has the following points. Right? And now with this, you can start taking this and putting it into sequence and then trending and collecting data, right? And if me and Mirza was just on the call earlier, we just spoke. If me and him both, and we're the biggest companies out there, and we both used brick, and everyone's using brick, there would be no issue. But that's not the case. Some are using haystack, some are using brick, right? So the goal, or sorry, the solution to this, when it got started, but it's a little bit, you know how ASHRAE works. They put out a standard 2-3P, and the P is for proposed, okay? And they should put a P extended, because I don't know where they are right now with this, and ASHRAE takes their time with everything, but they proposed a standard that harmonizes between different ontologies, different semantic data models, right? So to give you guys the option, right, hey, if you use this, everyone should be using it. All your data should seamlessly interact, right? So with 2-3P, they're harmonizing haystack and brick data models together, right? So they're telling people, if, you know, everyone should move towards ASHRAE standard 2-3P when you're modeling your data. Okay, so it's explanatory. I hope that made sense to you guys, because that all feeds into the next section here. Right now that we have modeled our data, we can now put a proper sequence of operations together and then reference those different points or parameters in the system using that data model. Right now we have trending, scheduling, and work. This is the end goal. This is the reporting. This is the optimize, right? After you made your building. So trending. Right. So a trend in a building automation system is a data point sampled over time or based on a change of state, or change of temperature, or it's sampled over time. So in 15-minute intervals, 5-minute intervals, right? When you're trending that specific temperature, humidity, whatever you need, right? So a couple of benefits of trend analysis, right? You can identify inefficiencies like simultaneous heating and cooling, right? You don't want your air handling unit to be going into both those modes at the same time, or your building is asking for heating or cooling at the same time, which doesn't make sense, depending on the weather outside, right? Or you can optimize system performance, right? By understanding how those building systems perform over time, operators can make adjustments, right? And you can improve the efficiency and comfort, for instance. Trending can also be used for other purposes like predictive maintenance mentioned earlier, right? Those are all things also that are going to be talked about with Jason in efficient solutions presentations. Predictive maintenance, occupancy optimization, or estimation, right? And then comfort monitoring. Those are all things that trending can do. We're going to take a look at this trending example here. And these examples are all courtesy of Christian Nazoff from the line of marketing. So this is a trend log. So there's a couple of trend logs that I'm going to show here, but all of these are from an air handling unit that typically in this specific scenario works in tangent with a chilled water control valve, right, to supply specific supplier temperature to the space. Now, a couple of disclaimers: the sequence of operation has to be checked, right, properly to confirm the enabling and disabling conditions for temperature control and operation. Right, this is going to help guide the process of selecting the right data points for trend. Right? You can't just trend every point and put it on whatever intervals you want. It has to be necessary to actually optimize the system. Right. To add more context to this air handling unit sequence of operation, in this case, we're going to outline the parameters of the economizer and chilled water control. Right? Differential dry bulb economizer control was implemented here. Right now, a word of caution to those using older sequence of operations: ensure your climate zone aligns with the economizer strategy. In economizer control, there are various strategies deployed by designers depending on the local climate. ASHRAE 90.1 sheds light on the different control types, like fixed dry bulb, differential dry bulb, fixed enthalpy, etc. For this case, the dry bulb economizer control sequence is enabled and an outside air temperature of 55 degrees, disabled at 70 degrees, and only at points in time in which the outside air temperature is below the return air temperature. The economizer damper is dedicated to maintaining the supplier temperature. We're going to show that soon. A set point of 60 degrees Fahrenheit. Because this is an integrated economizer, there are periods of time in which it works in tandem with the chilled water control valve to support the supplier temperature control towards set point. There is your supplier temperature trend log, right? And all these are trended over 15-minute intervals, right? Both of these. So two important terms to define. Again, I mentioned earlier, change of value trends and trend intervals. Again, change of value is if it's trending depending on the set point change, right? But in both of these scenarios, these are trend intervals. Both of these are trended over 15-minute intervals, okay? Now, the things like set point, whatnot, you can trend all of these every time they change, but in this case, we're just going to look at the change if it happens over a period of time. So at first glance, these two trends may not pique any interest, right? Chilled water control valve signal appears to be normal, right? Aside from some spikes early afternoon, and that can represent an influx of people coming back from lunch and whatnot, right? The only thing is, a huge focus here is to consider this carefully because we're looking at 50-minute intervals, right? So this spike, right, the 50-minute intervals are really a snapshot of what's happening. Right. So the spike with the temperature spike as well can actually indicate a deeper issue, right? Because at no point during the day, disregarding the supply fan motor heat, is the supplier temperature at or below the set point, right? So then now we're going to adjust the trend interval from 15 minutes over the day to a total of 15 minutes, but really using 1-minute intervals, right? Now we're really getting granular with the issue, right? Now you can see that in every one of these spikes, the control valve is constantly changing position, right? So this is a symptom of control valve hunting. Right? So system's inability, to summarize here, system's inability to provide stable supplier temperatures can be a symptom of an improperly tuned control. And if not investigated, could lead to premature failure of control actuators. So essentially, you didn't think really, is there anything going on? But with the context of the example of the air handling unit, now you know that that shouldn't be happening, right? There wasn't really a huge call for cooling, right? But somehow the control valve is going crazy, switching position. Now we're going to talk about a topic called scheduling, right? And all these are necessary back at your operating workstation, right, to allow the system to run properly. So scheduling in a building automation system is crucial for several reasons. One of those is energy efficiency, right? Again, repeated terms, but by scheduling the operation of your system, your HVAC, lighting, and other systems, building automation systems can ensure that energy consuming devices run only when needed, right? This is going to reduce energy waste and lower utility costs. You have comfort and convenience, right? Automated scheduling is going to maintain optimal indoor conditions. Maintenance and longevity, right? You're going to reduce wear and tear on equipment, right? By scheduling them to work only, scheduling your handling unit to open before school starts in the morning, 7 a.m., your morning warm up, and then cool down to the students' answer because it's already that's operational efficiency. We're going to simplify the management of the systems by automating routine tasks, taking that off of the facility managers, right? They can focus on more critical issues. Examples of that are HVAC scheduling, right? We have office hours, program the system to start heating or cooling an office building around 7 a.m., shutting down by 6 p.m. on weekdays. That's going to ensure the building is comfortable only during when needed, right, or occupancy times. You also have scheduling of your lighting system. Schedule the lights to turn on at 6 a.m. and off at 8 p.m. Right? And then again, we mentioned daylight sensors. Integrate those daylight sensors to adjust lighting levels based on natural light availability. Scheduling the locking and unlocking of doors. For example, the main entrance doors can be unlocked at 8 a.m., lock it at 5 p.m. All right, with restricted access outside those hours. And then overall, you can schedule routine maintenance. Right, you want to make sure that regular maintenance of things like boilers, chillers, and pumps are taking place. Right, set a monthly schedule for system diagnostics and performance checks. Alarm. So alarm is going to help you identify problems early, right? Such as equipment malfunctions or system failures. This also kind of feeds into the predictive maintenance, but you have to set a certain way. So this is going to allow for prompt corrective actions before they escalate into major issues. Alarms will also alert building operators to hazardous conditions like fires, gas leaks, or critical system failures, and it's going to ensure the safety of the occupants. Again, operational efficiency. Right? So it's going to tell the operator of any deviations from normal sequencing. It will also maintain optimal performance and prevent energy wasting. And again, preventative maintenance. And of course, a lot of these standards are actually specified. So you have to comply by specific alarming standards. So again, this is...
Thank you.
So again, you want to comply by those standards when you're specifying your system. So these are steps for you as a specifier to take while you're building your specification. So examples of these, right? You're setting high and low temperature alarms, right? An alarm triggers if the temperature is in a critical area, like a server room, or if it exceeds or drops below certain thresholds, right? That's going to prevent equipment damage. You have your general HVAC alarms, right? It's going to notify you when an air filter needs replacement, right? That's going to ensure air quality and system efficiency. Water leak detection, right? Mechanical rooms or under raised floors. It's going to trigger an alarm to prevent water damage and mold growth. Security alarms, right? Alarm is going to trigger if there's an attempt to access a restricted area right? It's going to enhance building security, or if a door is left open for an extended period of time. And last but not least, it's important to, while you're specifying, while you're thinking about these alarms, you want proper alarm. You don't want just repetitive alarms bugging you, right? Or redundant alarms that don't make any sense. Right? Think of that trend log example with the chiller. Imagine that chill water valve every time it switches position and asks for 100% chilled water. That should probably be an alarm, right? And I know the valves are rated for 100% open, but you shouldn't need 100%. The valves to be 100% open all the time. Right, so that should probably be an alarm. But now imagine you're getting that alarm every minute and then it goes away. Right, so you have to fine tune your system, right, to allow for proper alarming as well. This is also something that can be done through AI and artificial intelligence. So again, another reminder: sign up for that AI course after you do. Last but not least, we're going to talk about a couple of things before project delivery. We're reaching the end here, so we're right on time. Commissioning, testing, and documentation.
Okay.
So.
Sorry. Gracias. ¿Cómo sé cuál es mi cuenta aquí en Google?
So when it comes to commissioning, right, you want to verify sensor and actuator functioning. You're making sure that all this stuff is calibrated. So accurate sensor and actuator performance, right, it's critical for effective control. Calibration is going to ensure that your sensors will actually provide reliable data within the specific tolerances that you specify, right? And that the actuators respond precisely to the controller commands. And that's going to minimize the errors in system behavior. Response testing is, you're activating each sensor and actuator to verify they react appropriately to the commands from the automation system. For example, testing might confirm that a temperature sensor accurately triggers a fan or that a valve opens when the system demands. The step is actually going to confirm that devices are responsive and ready for operation. So you can't just write up the sequence of operations and set the hardware out in the field, walk away. You have to actually test the things. Things go wrong all the time. Equipment can come malfunction from the factory, or if not tested properly. Commissioning is going to ensure that controllers are configured correctly and ready for operation. Right. So you're going to look at each controller. You're going to verify the initial settings, load control programs. And this can actually be done simulated in a simulated condition as well. Actually, I think there's a mention of that soon. So you're going to conduct functionality checks, and you're going to confirm each controller's readiness, and you're going to ensure that the load automation system can perform as designed. Communication testing, right? Repeated a lot yesterday. Protocols, right? BACnet, Modbus, to make sure that each controller is actually communicating properly over the designated protocol, right? This is going to make sure that all components, the controllers, the sensors, and actuators are interacting seamlessly within the BAS network. And you're also allowing a smooth information flow and coordinated control. We also want to go back to your sequence of operations and validate all the sequences, make sure the control logic makes sense, make sure that you have specifying, make sure you have what your owner, what the building, the customer actually requested. They want control of these specific parts of the building. And you as a consultant, you're telling them, listen, you should probably include, these sections. We probably want to monitor this. Maybe you want to avoid local 197 fines and things like that. Those are all steps. Those are all necessary, right? And you can achieve that through a proper sequence of operation. Now, simulated testing, as you mentioned earlier, you can play the scenario before it gets to the field. You can run simulations on controllers before they actually make it on the field. You can simulate certain conditions, changes in temperature, humidity, demand variations, right? You can run these scenarios in a controlled environment before it makes it out into the field. Now, overall, you have your sequence of operation, which is a part of a huge specification document, right? Which is it's a guide detailing every aspect of the building automation system, right? And that's going to include network architecture, controller settings, right? Then your sequence of operation, your device integration requirements, right? Maybe your security requirements. We mentioned backend secure connect yesterday. Maybe you're going to specify backend secure connect. This is all going to be a part of your specification document. This document is going to lay out all the components, roles within the system, connectivity requirements. And this is going to, again, allow for seamless installation and operation. Then you have details on installation, right? So the specifier is going to make sure that there's a document showing how to actually install each item, right? Each product controller, and it's going to make sure that for future maintenance, the building operator knows what to do, how to troubleshoot future issues. There is, again, it's kind of repetitive here, so you're documenting, again, your sequence of operation for all major systems, right? And then you're creating maintenance and troubleshooting that. Okay, right? You're doing routine checks. You're specifying that stuff as well, right? You're going to define and specify regular checks for sensors, actuators, and controllers, right? This is going to make sure you have your customers' best interest at hand. You want to make sure that their building does not run into a lot of downtime because things are not calibrated or things are not checked regularly. Right? And you're going to create calibration schedules, right? And recommended calibration schedules. These are, again, part of some standards that are out there, right? You can follow that, or if you want to take it a step ahead, if you look at things like, Guideline 36 will help you really build that spec, really build that sequence of operation. So, and then you could also put some troubleshooting tips, right? Based on experience, based on that specific product manual, right? Troubleshooting tips for that controller, things like that. To summarize here, so we started off with the sequence of operation, right? Selecting, the correct control logic, the correct set points, the proper field devices that are necessary to control the system, right? That's going to help your system operate properly. So we went through the sequence of operation of all the systems, made sure that the lines made sense, and we took into consideration safety, things like that. Then we talked about standardized data modeling and tagging, right? And that's needed in order to actually use the data, right, after we automate the building, right? And again, automation is not your end goal, right? It's throwing the hardware, making everything run on a cycle is not the end goal. Trending, scheduling, and one are the key to a fully functional BAS, right? When you trend points, that's where you start indicating future failure. That's when you start knowing if your system's actually operating at the intended set points or certain conditions, right? Last but not least, proper testing, commissioning of all devices is needed before delivery of a project. That's the BAS series 101 for 104 recapping here. So I hope you guys enjoyed it, and if you have any questions, I'll be here.
Questions? Oh, there's a question in the chat there.
Tips or reference documentation you can present along to class. So that's a loaded question, but so that has to do with what you're trying to achieve, right, for your customer. So it's not, there isn't one document out there that will tell you if the building is actually, returning on investment properly. But the best way to do that is probably partner with an engineer, right, that's doing energy auditing, right? I've heard of scenarios where vendors are working with an engineer to do energy auditing on the building, figure out what the building needs, right? Figure out what the building automation costs or what is actually needed to get the building to where it needs to be. And then we look at the cost spent versus the energy savings over the next couple of years until you get that return on investment. And that's really the first step. But again, there isn't a standard document out there. There probably is several of them. Let's talk offline. I can probably point you in the right direction where we can get that process started.
Yeah, I think it also really depends on what you're looking for and what strategies the customer would be looking to implement. So whether you're just saying like any tips based on, using a certain sequence of operations or using a certain, energy metric or energy modeling like Moose was talking about. But we do have some like case studies that we can point you towards, especially like research projects. So if you look on ASHRAE's website, they have a lot of research projects, which are what usually go into creating a lot of these standards and guidelines, and every time they do updates. So that's a really good resource. We have a few locally, like Moose said, he can kind of point you towards a few of those, but even just things, of new control strategies that are in place that we're running with folks up in universities in order to show those ROI savings from, point A to point B. So we have some of those. I think it would just depend on what you're actually looking for. Like when you talk about ROI strategies, like what you'd actually be implementing, because we've talked about a lot. Yes,
Hi.
no problem.
I have another question regarding
Sure.
the pumps. Slide we were talking about the chill water pumps being lead lag, and these days we get pumps with smarts built in that are capable of having that lead lag automatic switch over. Typically, like what we'd want to see is BAS have command of those pumps through physical hardwire start-stop, but what do you think about the smarts built into the pumps? Would that be useful just to use and monitor? What's the difference between the hardwiring and just using the inbuilt smarts of the pumps?
VFD versus just getting what's shown here, enable and status, hardwiring it versus taking it to a communication via the VFD.
Yes. So like some pumps, like the Armstrong pumps, they have the capability to just choose a mode of operation and just run the pumps based on what's being selected rather than being hardwired into. Would that be more useful than specifying pumps to be hardwired to the DTC here?
It's shown here versus collecting that from from the VFD.
Yeah.
Good answer for that, just based on my experience, because I don't really write tons of sequences, but I think it's very efficient to do it through the VFD for one reason, because when you run that wire, running an 18.8, right? 2 for AC2 for power, AC2 for turning on the this is the pump, turning on the pump, right? So you got 4 points. You have fault, turning on the pump, controlling the pump speed. That is your best bet because you're running one wire. If you run an 18.4 and just hardwire it, but you're not collecting anything from the backend interface, you're actually missing out on points, right? Also, when you do it through the VFD, this shows up automatically kind of as a backnet point on your system, right? So if you have a friend or if you have an operating workstation, the VFD will show up if it has a backnet interface. Right? So that helps in programming. It helps in running your sequence of operation. So the most efficient way I've seen it is just doing it. If there's a VFD, utilize what's there, right? If there's an actual backend interface, connect it, pull the communication point to the backend interface, right? It's hardwired anyways, by the way. I don't know if you like a distinction between one being hardwired and one is not. But you mean like wiring up the current switch and not pulling data from the VFD? I think the way I've seen it is it's usually done at the VFD if it's available. So versus there being a motor there or just wiring up to the current switch.
I think also maybe what you're asking is using the functionality that's built into the pumps itself, right? Instead of like wiring it into the control system itself, like Moose was saying. And I think the only disadvantage that I would say is going to be like if you can't tie in the features like Moose was talking about, like alarming, and it might also create more of like a maintenance task. So then you might not be able to do slight changes or maintenance on your BAS system itself. So if it doesn't integrate natively from those onboard pumps into your BAS system itself. I don't know that there's like a lot of disadvantages, but I would think that was probably like your biggest one would be it's almost like it would be a redundant effort to have somebody that can go out and make changes to the pumps themselves, or if you tie everything into your BAS system, you're able to do that a little bit more easily and have that integration feature to be able to like monitor alarming and all of that type of stuff, if I'm thinking about your question correctly.
Yeah, that's it. Thanks, Emily.
Yeah.
So you're saying wiring directly to the DEC system. In both scenarios, you're hardwiring to the controller, whether coming from the VFD or coming, and there is no VFD, and you're just wiring to the current switch and relay, making sure that the pump is on and make sure that it's actually working. So I don't, like Emily said, there isn't really much disadvantages besides the fact that it's just much easier to do it through the VFD because you're also collecting more points, and then you're able to run, do the calculate virtual points like runtime, right, by monitoring the VFD, right? So there's kind of a disadvantage of not doing, not using the available VFD backend interface if there is, that it comes down to that. It comes down to the. So. Any other questions? No, absolutely not.
I have one question.
Sure.
So for the you said having a troubleshooting and maintenance guide. Were you talking about for like physical HVAC equipment or for like BAS conversions?
This is about even if you're making a new system, if you're putting a new building automation system, or if you're retrofitting, it doesn't matter. There's still going to be a sequence out that as a consultant you're designing, you're going to create a maintenance troubleshooting guide for the equipment that's going into the field. So start pulling in data from that site, right? Whether you're retrofitting or whether you're creating a whole new building automation system. I don't think it matters whether you're converting from another system. In all scenarios, you should have a maintenance and troubleshooting guide, right? Because someone's going to be monitoring that system. Someone's going to be sitting in front of that operating workstation, and you want to give them tips on how to manage that system, right? Whether that vendor or controllers you're using in that space is tying into a master head end that's using a different vendor's controllers, you still want a maintenance and troubleshooting guide. That will usually come also from the manufacturer of the retrofitted control space.
Yeah, so I think what he's saying too, and just you kind of want to have like a hybrid between, including like a comprehensive guide for your BAS system, right? That'll include more along the lines of your system architecture, your network diagrams, your communication protocol, kind of those maintenance schedules, what some of those alarms might mean. But then the field manuals are what's going to be for the device specific procedures. And those will come from, like Moose was saying, when you ran through that diagram that had the chillers on board, because it would come from a manufacturer. So those packaged units are going to have kind of those device specific procedures. But I think it would be helpful to have both. So kind of the hybrid example there. And oftentimes too, they'll have like quick references for like code errors that are actually on like the prepackaged stuff. So it's kind of the hybrid.
Got it. Thank you.
Okay, we're kind of running a little bit lower on time yesterday. I think we, got a little bit started late here. So our guideline 36 is scheduled to start around 1:15. But again, we've kind of truncated to make sure that we have all of the time for our technical difficulties. So we're going to have everybody come back on around 1:15. We probably won't start until that 1:20 timeframe, just to give folks a little bit more time to get started. Guideline 36 is going to be myself and a guest presenter, Jason Bursill, who will join us here shortly. So with that, we'll see you guys back here in about 5-10 minutes.
Thank you, guys. Thank you.
We're just gonna give it just a little bit longer here, maybe about 5 to 7 more minutes before we get started for real.